in this lecture we will be looking at the pulsatile flow. As we know that the flow in the cardiovascular system is pulsatile. We have on an average in a healthy human being about the heart beats about 72 times per minute. So the flow process or the circulatory process repeats itself about once per second. The frequency is about once per second. So the flow is not steady as is assumed in the Pulsatile flow, for example. Rather, the pressure gradient or the pressure that drives the flow in the circulatory system, it changes almost every second, and it is periodic in nature. So the flow is pulsatile and periodic. So in order to understand or in order to study the flow in the cardiovascular system, it is important that we understand and we know what is the flow in the pulsatile flow in a rigid channel, for example. So that is what we are going to study in this lecture. Okay. Now what we see in this graph here is the pressure gradient dp by dx versus time. This is a typical pressure versus time diagram in the circulatory system. So the pressure goes through certain changes. It peaks first, the pressure gradient is highest first, and then there is a dip, and then again a bit increase, and then the process repeats itself. So the pressure gradient is pulsatile. The pressure is pulsatile in nature, it is periodic in nature, it's time dependent, it is not steady, and same goes for the pressure gradient. So we need to study that because the flow is driven by the pressure gradient in the circulatory system, and the pressure gradient, they are time dependent, they are pulsatile, they are periodic. So the associated flow is also going to be pulsatile, it is going to be periodic in nature, and it will be time dependent. So while this graph is periodic in nature, it is of course time dependent, but by just looking at the graph we cannot guess the function or time dependent function that the pressure follows. So here we might recall from our undergraduate classes that any periodic function, say ft, which has a time period of t, it can be represented as a sum of one constant term and fundamental of period t and its harmonics. So a periodic function can be represented as a sum of ft, can be represented as a constant. So let us say this constant is a0 plus some cosine terms, let us say a1 cos omega t plus a2 cos 2 omega t plus so on, plus b1 sin omega t plus b2 sin 2 omega t plus so on, where omega is the frequency and the unit is radian per second. It can be 2 pi over t, where t is the time period. So now these any signal which is periodic and time dependent, that can be represented as the sum of a constant term plus sine and cosine terms, and these constants a0, a1, a2, b1, b2, they can be evaluated by different methods. One of the methods is where, for example, one calculates that a0 is equal to 1 over t integral 0 to t ft dt, and similar terms for a1 and b1. There you will have 2 by t 0 to t ft sine omega t dt, and so on and so forth. Okay. So the point I am trying to make here is that a periodic signal which is arbitrary can be decomposed into sinusoidal or sine and cosine terms. Now these sine and cosine terms, the coefficients of these sine and cosine terms can be obtained by using Fourier transform. Okay. Now, as you might remember, that sine and cosine terms can be also represented as a complex exponential term. So you can write e to the power I theta is equal to cos theta plus I sin theta. So for differentiation and integration purposes, it is easier to represent the Fourier series in terms of exponential term. You can write e to the power I theta is equal to cos theta and I sin theta. And so let us say that the pressure gradient del P over del Z can be represented as sum of an, which is a coefficient, into exponential term e to the power I n omega t, where n is an integer which value will change from 0 to infinity. At n is equal to 0, the first term will be constant, and e to the power I n omega t. So a n will be a n minus v n, if we want to relate it from the previous terms. Okay. So the pressure gradient can be represented as the sum of different harmonics. Harmonics are n is equal to 1, 2, 3, 4. Can be represented as a sum of the harmonics. So our target or our goal here now is to understand or to obtain a relationship for pulsatile flow where the pressure gradient is, say, exponential, and the del P by del Z is del P by del Z constant, and into a function of time, which is exponential function. Okay. So we will start with the conservation equations that we have been doing as of until now. The mass conservation, which is also called continuity, momentum r, theta and z. So you see they are all in cylindrical coordinates, and the stresses, the equation has been written in terms of stresses. We will assume the flow in a cylindrical tube, and flow is in the axial direction. So the flow is going to be axisymmetric, and when flow is axisymmetric, that means v theta is equal to 0, and the terms, the gradient of the variables in the theta direction will be 0. So this will end up that we will not have any term in the theta coordinate, and the respective or v terms containing v theta or del by del theta or the gradient in the theta direction will be eliminated in the equations r and z directions also. So we will end up this set of equations for the axisymmetric continuity r and z, and so this continuity equation we have only two terms, del b by del z and the radial term, and similarly in r and z directions. Now we assume at this point that flow is fully developed. So if the flow is fully developed, then we might recall that del Vz by del z, that is the gradient of the axial velocity in the axial direction is 0, or the velocity profile does not change along the axial direction. So if del b by del z is equal to 0, then from here we can see that Vr is also going to be 0, or if we assume Vr is equal to 0, so if Vr is equal to 0, then this term is going to be 0 and del b by del z is equal to 0. So we have two conclusions from here, that the flow is fully developed and Vr is equal to 0. So we are going to neglect the terms. Remember that Vr is equal to 0, so this is 0, this term is also 0, Vz is there, but Vr is equal to 0, so this term is also 0. Now because this term has Vr, so this term will go to 0 and this term will also go to 0. So effectively what we are left with is minus 1 over rho del p by del r is equal to 0, where rho is non-zero, so we will have del p by del r is equal to 0. In this, the z momentum equation, we have del v by del z del t, it will be non-zero, but this term will be gone because Vr is equal to 0. Again the flow is fully developed, so this term is 0. This term will be there, but again del v by del z, del Vz by del z is equal to 0, so this term will also be 0. So now we will have our momentum equation in the r direction, which is del p by del r is equal to 0. So that simply tells us that p is independent of r. P is not a function of r, and p is anyway not a function of theta. P is a function of time and p is a function of the axial direction. So p is a function of time and p is a function of z, and for the z direction momentum equation we have del Vz over del t is equal to minus 1 over rho del p by del z nu 1 over r del by del r r v del r del Vz by del r. So there are three terms. This is transient term, this is pressure gradient term, and the third term is the viscous term. So effectively now we are left with the Vz term. Let us non-dimensionalize the terms in this Vz momentum equation, and the scale for non-dimensionalization, let us take a velocity scale v to non-dimensionalize velocity. Both the length or the distance terms r star and z star are non-dimensionalized by the general radius, so r by a, z by a. P star pressure will be non-dimensionalized by the dynamic pressure rho v square, and t is non-dimensionalized by the time step or say frequency, so it is omega t. Now we substitute this in the equation, then what we will get is del Vz star, and it will be multiplied by V divided by del T star, and it will be omega will come from here, is equal to minus 1 over rho del P star. So because of P star you will have rho V square term there divided by del Z star. So for Z star it will be multiplied by A plus nu. Let's collect all the terms of A here. So we will have 1 over R star, and there will be 1A for R star, del by del R star, and this will be A square into, there will be 1A for R in the numerator and another A for R in the denominator. So we will have both of them cancelling out. So we will simply have R star del by del R star now. For Vz we will have Vz star and 1V here. Let us now eliminate some of the terms. So we can make this 1. So we can multiply by A square over nu V. If we do that, then we will have first term as omega V will cancel out, omega A square by nu into del Vz star over del T star is equal to, so when we multiply this by nu, rho and rho will cancel out, A square, so there will be only 1A because 1A will cancel out, and only 1V divided by nu. So you might have recognized this non-dimensional number by now, and this is multiplied by, there is a minus sign here, del P star by del Z star plus nu square A square by nu V, and this will be 1. So we will have simply 1 over R star del over del R star del Vz star over del R star. Okay, so we can see that there are two non-dimensional group, whereas this is Re or Reynolds number, and this group is a new dimensionless group which is known as Wormsley number. Okay, so Wormsley number, if we look at it, is represented by alpha square. This alpha square is equal to omega A square by nu, as we have seen in the non-dimensionalization of the differential equation, and if we rearrange it, then it turns out that it is a omega into a by nu. So a omega is a velocity scale, and a is the length scale and nu is the kinematic viscosity. So it resembles a Reynolds number, and this velocity scale is the oscillatory velocity. So it is the ratio of inertial forces and viscous forces, but this inertial force is the oscillatory inertial force and the viscous force. So this is not flow, this is force. You can also rearrange it. Alpha is equal to a over omega, nu over omega. Sorry, this should be nu over omega, and this is you might see that nu over omega, the units there, nu is meter square per second, and omega is also 1 over second. So second will cancel out, and nu over omega is equal to meter square. So this nu over omega power 0.5 is going to be meter, and this is oscillatory boundary layer thickness. So alpha is also a ratio of the channel radius and the boundary layer thickness. So that says that at low Wormers-Lee number, the viscous effects are going to dominate and the boundary layer is going to be thick, whereas at large Wormers-Lee number, the boundary layer will be thin and alpha will be large. So when alpha is large, boundary layer is thin, viscous effects are negligible. Okay, we will come back to this. So anyway, after non-dimensionalization, if we go back to our equation, this equation has been written again in this form. Alpha square del V Z square over del T star, del V Z star over del T star is equal to minus RE Reynolds number del P star by del Z star plus 1 over R star del over del R star del V Z star over del R star. One might be worrying about that the Reynolds number is generally dependent on or defined in terms of the radius. So one can do that, and then there will be a 2 term coming in picture there. So as I was talking about, that if alpha square is small, then in that case the viscous term will be significant, but when the alpha is small and it is less than 1, then alpha square will be further small and this term will go away. That means at low Reynolds number, it is not, this term is 0. So you will have that the pressure gradient term, the pressure gradient term and the viscous term, they will balance each other. Whereas if the inertial force is high or the Wormers-Lee number is large, in that case the viscous force will be negligible, or the viscous term the viscous term will go away. You can take this on this side and then one can see that the viscous term will go away, and the viscous term goes away, then the transient inertial term or the oscillatory inertial term that will be balanced by the pressure, or pressure gradient will be balanced by the inertial force or the transient inertial force. So okay, now our objective is to understand or to find out a relationship between the pressure gradient and flow or say axial velocity, because v theta is equal to 0 and Vr is equal to 0. So, the only direction in which velocity is non-zero is the axial direction. So, then we can integrate it to find out the flow rate. So, our objective is to find out that what is the flow rate, the relationship between flow rate and the pressure gradient. So, let us assume a harmonic pressure gradient that del P by del Z is equal to del P cap by del Z e to the power I omega t, and we because the pressure gradient is harmonic. So, the force coming from this, let us assume the solution is Vz is equal to Vz cap I omega t. So, our objective is to find out this Vz in terms of the pressure gradient. Okay. So, first we will look at the two asymptotic cases. The first one where the Womersley number is small. So, as we discussed just few minutes back, that at low Womersley number, when alpha is small, that means the inertial term is negligible. So, when we neglect the inertial term, what we will end up with that the pressure gradient is balanced by the viscous term. So, this term will go away and we will have del over del R of R del Vz over del R is equal to 1 over rho into nu, which will be mu, the dynamic viscosity, into del P over del Z, and we have, I think, missed one R here. So, 1 over R, when it goes here, it becomes R here. Now, we substitute that del P by del Z is equal to del P cap over del Z e to the power I omega t, and similarly for Vz. So, we can also substitute Vz is equal to Vz cap e to the power I omega t. If we substitute both of this in this equation, then we will get del over del R, R Vz cap over del R, because e to the power, the exponential term does not depend on the radius. So, we can take this out of the differentiation, equal to R over mu del P cap over del Z e to the power I omega t. Now, because the exponential terms, they can cancel out, so we will just write this and integrate it, and what we will get is R del V Z over del R is equal to, we have missed a, no, this is correct, R del V Z over del R is equal to R square over 2 mu del P cap over del Z plus a integration constant, let us say C1. Now, we take this R on the other side, so let us delete this, and this will go away and we will have C1 by R. Now, this C1 has to be 0 as del Vz over del R is finite at R is equal to 0. So if we substitute that, then C1 is going to be 0. So this term will go away, and then we further integrate it. So we will get Vz is equal to R square over 4 mu del P cap over del Z plus C2. So Vz is equal to R square by 4 mu del P by del Z plus C2. And now we use the boundary conditions. So we had Vz cap is equal to R square over 4 mu del P cap over del Z plus C2. We need to find C2, and the boundary condition, no slip boundary condition on wall, which says that at R is equal to A, which is wall, Vz cap is going to be 0. So that means this is 0, and A square by 4 mu del P cap over del Z plus C2. If we subtract these this equation, let us say equation B and equation A, and if we do B minus A, then we will end up with Vz is equal to minus, because it will be minus, so we will do B minus A. Vz is equal to minus 1 over 4 mu del P cap over del Z and A square minus R square. So if we substitute this in Vz, you remember we had Vz is equal to Vz cap e to the power I omega t. So we will have Vz is equal to minus 1 over 4 mu del P over del Z A squared minus R square into e to the power I omega t. Now you might see, because of this negative sign, you can say that this term and this term, they make the pressure gradient. So because of this minus sign, Vz and del P by del Z, or the flow velocity and the pressure gradient, they are out of phase, 180 degree out of phase. So they are completely opposite. This is the relationship that we just derived. And if we plot del P by del Z, which will be a say sinusoidal function, it is 0.5 t by t, it is minimum, and then it is say 0 at this. Now so it is at dp by dz is equal to 0, it is 0, and then it is maximum at t by t, so it is going to be sinusoidal function anyway. So at the minimum, when dp by dz is minimum, it is negative -1, then at that point you will see that the velocity is in the forward direction and parabolic velocity profile one obtains. When dp by dz is maximum, then the velocity is in the negative direction and the entire velocity is negative at every point. Whereas when dp by dz is equal to 0, then the velocity is also 0 at 0.75, you can see, and same for 0.25. So they are the velocity and dp by dz, they are 180 degree out of phase. Okay. One can also write this as vz is equal to -1 over 4 mu a square minus r square del p by del z. So del p by del z and vz, they are out of phase. Okay, let me not confuse you from this sign. Okay, so we have looked at asymptotic solution at small Womersley number, which suggests that it's small Womersley number. The expression is very much similar to what we have for a Pulsatile flow, but the velocity and the pressure gradient, they are out of phase. Now let us look at large alpha, or when Womersley number is large, then as we suggested that as at large Womersley number, the inertial forces will be dominant and the viscous forces can be neglected. So this viscous force can be neglected. As we followed earlier, let us substitute Vz and del p by del z here. So we know that Vz is equal to Vz cap I omega t. That gives me that del Vz over del t is equal to, sorry, this is Vz cap e to the power I omega t, and del Vz over del t will be Vz cap I omega exponential I omega t. So let us substitute this here, and what we will get is I omega Vz cap exponential I omega t is equal to -1 over rho del p cap over del z exponential I omega t. Now I omega t will cancel out, and what we will have is Vz cap is equal to -1 over I rho omega del p cap over del z. We can change -1 to I square, so we will get I over rho omega del p cap over del z. So what we see from here, that in this case velocity is plug flow, that is, there is no gradient of velocity in the radial direction. The velocity is uniform, and which is understandable because the velocity profile comes because of the viscous term, and we have neglected the viscous term. So the velocity profile is plug flow. Okay, and as you can see from this, that this term has I, so the velocity Vz will be 90 degree out of phase, or 90 degree phase difference between the pressure gradient and the flow velocity. So as you can see from this graph here, the similar graph for the pressure gradient as we saw for small alpha, and for velocity at large Wormsley number, we can see the velocity profile is parabolic, and wherever there is velocity is maximum, the velocity wherever the pressure gradient is maximum, on those places, maximum or minimum, the velocities are 0 there. Whereas when the pressure gradients are 0, or when the pressure gradient is 0, at those time instants velocity have a magnitude as maximum, and the velocity profile is plug flow. That means the velocity is uniform everywhere in the channel cross section. Okay, so now having looked at the solution at two asymptotic limits, when the Wormsley number is small and when the Wormsley number is large, let us look at the solution and try to find out if we can find the solution for the entire range of Wormsley number. So we again come back to the Vz momentum equation that we have obtained after reducing the Navier-Stokes equations to the axisymmetric ones, and then neglecting the terms based on that Vr is equal to 0 and del Vz over del Z is equal to 0, that is flow is fully developed. So then we have got this equation. Now in this equation, as we have been doing earlier for the two asymptotic cases, let us now substitute Vz and del P by del Z. So if we do that, again we will have del Vz over del T is equal to I omega Vz cap exponential I omega T, that is equal to minus 1 over rho del P cap over del Z e to the power I omega T plus nu 1 over R, and let us break this into two terms. So what we will get is into R del 2 Vz over del R2, and this R and R will cancel out, so we will just get rid of both of them, plus we will have 1 over R, and the differentiation of R is 1, so we will have del Vz over del R into e to the power I omega T. Now all the exponential terms in the three equations are same, so they can be cancelled out, and let us rearrange this to as a second order differential equation. So we can write this as this will be Vz cap, so we can write this as nu del 2 Vz cap over del R2 plus nu over R del Vz cap over del R minus I omega Vz cap is equal to, so because we have brought this on that side, and then it will be equal to 1 over rho del P cap over del Z. Okay. So this is the equation that we got in the previous slide. So now let us rearrange it to this equation. So first we need to divide by nu, and Vz cap is a function of r only, so we can have this as total derivative, so we can write this as d2 Vz cap over dr2 plus 1 over r d Vz cap over dr. This because we have been writing this as a function of r, so this is also a function of r. So dVz over dr plus, if we want to change this I to I cube, so minus 1 is equal to I square, so this will be I cube omega by nu Vz cap is equal to 1 over rho into nu, or we can also write this as mu del p cap over del z. So we have obtained this relationship. Now this is, if you look at, this is a linear ODE. All terms have power 1 only, and this is second order, and non-homogeneous. So we have to go back. If we want to find out the solution of this equation, we have to go back to our undergraduate mathematics, where we learned how to solve non-homogeneous second order linear ordinary differential equation. So if we go back to this, you might have heard or you might have read about Bessel equations. If you have done a heat transfer course where you have looked at some of the complex equations, there also you might encounter Bessel's functions. Otherwise you would have definitely done these in your undergraduate mathematics. So if the ordinary differential equation, a homogeneous differential equation, if it looks like this, x square d2y by dx2 plus x dy by dx plus x square minus n square y is equal to 0, and if we divide by this by x square and take n is equal to 0, so we will end up with d2y by dx2 plus 1 over x dy by dx plus y is equal to 0. This is a homogeneous equation, and when the equation is non-homogeneous, this term in place of 0 it will become non-zero. So now let us compare the form of this equation with the equation that we have derived. So d2y by dx2 d2vz by dr2 1 over x dy by dx 1 over r dvz over del r or dvz over dr plus I cube omega by v vz is equal to 0 if we take the homogeneous part of our equation. So if we want to have the similarity in the two equations, then we will need to change our variables a bit. So let us do that, and if we assume another variable, let us call this s, and if we assume that s square is equal to I cube omega by nu into r square, so then we can write this equation as, let us divide the entire equation by I cube omega y nu. So we will have 1 over I cube omega by nu d2 vz over d r2 plus 1 over I cube omega by nu into r d vz cap over dr plus vz cap is equal to 0. Now we have seen that s square is equal to, we have assumed that s square is equal to I cube omega nu into r square. So from that, let us just make this look better. So this is dr2. Now we can have this d2v z cap by d s2 plus 1 over s. There are two s here, also one here and one in the differentiation. So 1 over s d vz cap over ds plus vz cap is equal to 0. So now we have both the equations, the Bessel differential equation for n is equal to 0 and the equation that we have obtained for intermediate Vomelski number, they look very similar. So the next thing is to look at what is the solution of this ordinary differential equation. And if we look at the books, this is the form of the equation. For n is equal to 0, the xy differential equation will have the solution y is equal to a j naught x plus b y naught x, where we have a and b, they are constants, whereas j naught x and y naught x are called Bessel functions, and j naught x is the Bessel's function of first kind and y naught x is the Bessel function of the second kind. So if we look at the nature of the graphs or the values of this j naught x and y naught x, then we, with respect to x, then we see that at x is equal to 0, j naught x or the Bessel function of first kind is, the value is 1, whereas it is indefinite at x is equal to 0. That means y naught at 0 is indefinite, whereas our velocity at s is equal to 0, that means at r is equal to 0 will be finite, right. So let us write down the solution based on this, the solution for vz cap, and what we will have by copying from this, a j naught s plus b y naught s. Now at, as we have just seen that y naught 0 is indefinite, so b is equal to 0, so that this term goes away. So we have that vz is finite at r is equal to 0. So our solution is vz is equal to, or vz cap is equal to a j naught s. Okay. Now we have this because our solution, our equation is non-homogeneous equation. So what we have obtained is the complementary solution, and this complementary solution is a Vz complementary is equal to a j naught s. We can also find the particular solution, and I will leave it to you to find how to find out the particular solution, and this will turn out, it will turn out that Vz cap the particular solution will be I by rho omega del p by del z, which is the last term we had. So the total solution will be, or the complete solution for Vz will be, because it is a linear equation, so both the solution can be superimposed. So we will have Vz is equal to complementary solution, which is a j naught s plus Vz particular solution. So that is what the complete solution is. Now what we need to do, that a is unknown in this. Remember what was the particular solution? The particular solution we had is Vz p is equal to I by rho omega del p by del z. So we will use this later on, and we use the no slip boundary condition to find a. That means Vz is equal to 0 at a j naught s. We had s square is equal to I cube omega by nu r squared. That is what our definition of S was. So at r is equal to a, the value of S will be I cube omega by nu a squared plus V z p cap. Now from this we can also remember that alpha square, which is Wormsley number, is equal to a square omega by nu. So this is I to the power 3 by 2 omega power 1 by 2 and nu power 1 by 2, or we can say that alpha by a is equal to root of omega by nu. So we substitute this, then we will find a is equal to minus V z p divided by j naught I to the power 3 by 2. This will be, this will be a only, not a squared. So we will have alpha over a, and a will cancel out. So I to the power 3 by 2 a. So we will have Vz is equal to Vz particular, we can take this out, 1 minus, now we substitute the value of a here, so that will be j naught, and the s, if we replace s, then it will be I to the power 3 by 2. In place of root omega by nu, we can write alpha over a and r here for s, and this is divided by j naught I to the power 3 by 2 alpha. So this is the value of Vz cap, and the relationship that we can find out, what we have found is Vz cap, and the Vz will be Vz cap into I omega t. So this is the relationship between the velocity and the pressure gradient for pulsatile flow, fully developed flow in a rigid tube. We can also find out the asymptotic solution by replacing alpha is equal to for very small alpha and for very large alpha. So, in summary, today what we have looked at is that using Fourier series, any periodic signal, it can be decomposed into sum of sine or cosine terms, or what we call harmonics, and we will try to take, or we will try to do one example for this case. Then we have encountered a new non-dimensional number which is very important with respect to, or in cardiovascular fluid mechanics, which is known as Wormersley number. It is the ratio of oscillatory inertial flow or the oscillatory inertial force and the viscous force, and so it is kind of oscillatory Reynolds number. And then we have obtained the solution for pulsatile flow for a harmonic or for a sinusoidal function or for an exponential complex function for fully developed flow, assuming that we obtained, or we saw that at small Wormersley number, at small Wormersley number or low Wormersley number, the expression of the velocity profile is very similar to what we obtained for a Poiseuille flow, but it is time dependent and it is 180 degree. The velocity is 180 degree out of phase with the pressure gradient, whereas at large Wormersley number, the flow profile is same everywhere in the cross section, that is no effect of viscosity. Flow profile look like a plug flow, it is uniform everywhere in the cross section, and it is at 90 degree out of phase with the Wormersley number. So, wherever the pressure gradient, it is 90 degree out of phase with the pressure gradient. So, wherever the pressure gradient is maxima or minima, then because it is sinusoidal function, so when the pressure gradient is at maxima or minima, the velocity is 0, and if it is 0, then if the pressure gradient is 0, then the velocity is maxima or minima. We will also try to look at some of the applications and try to have a feel of numbers and some examples of the Wormersley solution in the context of cardiovascular fluid mechanics. Thank you.